Okay, we're starting. We're going to finish up exponential growth and decay and move on to related rates. So I have two examples to get through for this one. So just to review a little bit before we jump in here, this is just when a quantity changes at a rate proportional to its current size. Or changes by some fixed percentage amount per unit time. Okay, so that's when a quantity has that kind of change, we say it changes exponentially. If it's increasing, we say it's growing exponentially. If it's decreasing, we say it's decaying exponentially. Of course, there are these, the buzzwords, because on the third test, we're going to be doing several topics that will come to you in the form of a word problem, so you need to recognize when each one of these topics are showing up. So some things you would look at to know that you are looking at this kind of problem. Well, the actual word exponential will show up usually, or you will see the phrase proportional to its current size. Or you'll see the phrase something like radioactive. Usually it would apply to populations. You'll also see things like compounded continuously. So if you see there's a word problem that sort of starts off like, okay, there is a population that is growing at a rate proportional to its size. You know it's this, or there's a radioactive substance, and at this time there's this much of it, then it's this, or something like that. Or you deposit money in a bank and assume it's compounding continuously. It's not very realistic, but under that assumption, it means you would go under this topic, right? So you kind of would know that you're supposed to be doing this. And once you know that, some equations immediately take effect. So if P is the quantity, then it turns out that P prime would be proportional to its current size, so R is going to be a constant. You need to remember the name of this constant. It's on the handout. It's called the growth constant or the relative growth rate. So those two phrases would refer to this guy. This guy is called the rate of change or the rate of growth or just the rate of P. Okay, so they can be sort of described using similar verbiage, but the combination of the words used can be very different. So this is like the growth constant or the relative growth rate, where this is the rate of growth, or the rate of changes of the population. So this guy here was called the differential equation. So whenever you're asked for a differential equation, it means this is the guy that they're asking you for. You need to figure out the R and plug it in here. There is a solution to this, comes from the third formula, PE to the RT. So that tells you about the current size at any time. So T is time, this is your growth constant, P naught is your initial amount. You can also be asked for an initial condition, which is just an equation that tells you what the initial amount is. There's also a formula for the doubling time. So T with a subscript D is for the time for the quantity to double in size. Or time to triple in size would be ln 3 over r, and so on and so forth. Decay is pretty similar. The difference with decay is that now your rate is negative, meaning it's decreasing. It's a decreasing quantity. And so you end up with P is equal to P naught e to the minus RT. and you would also have TH, which is the half-life, the time taken to have half of what you started with if it's decaying. And that's also ln2 over r. So those are sort of the formulas. This is your differential equation. This is the equation for that gives you the current size of the whatever quantity you're measuring. And these two guys show up ever so often, talking about how long for it to double or how long for it to become half of what you started with. And it just depends on whether you're doing growth or decay. The formulas are very similar, except this one has a negative here and a negative power to indicate decrease. So that was kind of where we left off, and we did an example. And so pretty much you're going to be reading these problems, and they're going to describe a situation for you, and they're going to ask you a bunch of questions. And you basically need to know which one of these equations to go after in order to answer that problem. And we did one example from the handout. So now let's move on to the second example. Very familiar to the first, but I kind of want you guys to go with me on this to make sure we are actually understanding. So the half-life of a radioactive substance is 30 years. Suppose you have a 200 milligram sample of the substance, and P is the mass remaining after T years. Answer the following questions, okay? So when you read that problem, right, so I know it says exponential growth and decay, but on a test it wouldn't be titled that. The things that are going to hint you that it is an exponential growth and decay problem is the fact that there's the word radioactive there. They mentioned half-life, and they're talking about the size of something. So that's a classic exponential growth and decay problem. And is this growth or decay for problem 2?
Decay.
Huh?
Decay.
Decay. How would you know it's a decay problem? Because it says mass remaining? Okay.
It's a half-life.
It also says half-life, right? So once they say half-life, that's them saying, oh, there's going to be a point where there's half of what was there before. So that indicates a decrease. Also, radioactive substances actually will decrease over time. So there are a bunch of things that can say from you that now you know you're in this topic, and specifically you're looking at decay, which means this set of equations is what will take effect from now on, right? So in your head, you know that I'm going to be using one of these guys over here. So let's move on to A. So now it asks for the differential equation satisfied by P of T. How do you do that? What are we after? Differential equations. What? Well, you need the whole equation, so it's asking for this one, right? Now, the P is just going to be P. The thing is, to answer this question, you need to actually find the R, so you can plug it in here and write that down. So how do you go about finding the R? So once they say differential equation, you should realize that they're really asking you for this equation. But the R is the constant that you need to find. How do we find that? Yeah?
Use the half-life formula.
The half-life, right? There are several equations that have R in it. This one isn't very useful. That's actually the one we're looking at. This one's also not useful because I don't really know some other point in time where the quantity is. So I'm kind of left with this. They told me the half-life, and ln2 is just a constant, so I can actually use this to solve for R. Okay? So we know that the half-life is equal to ln2 over R. This would mean that R is equal to ln2 over the half-life. This would mean that R is equal to ln2 over 30 years. This means that P prime is equal to minus ln2 over 30 times P. That's our differential. Find a formula for P of t. Okay, what's the formula for P? The Bird formula. So B said find P of t. So we know that P is equal to P naught E to the minus RT, because we're dealing with decay here. So fill in the numbers. What do we get?
30.
Huh?
30. No, 200. 200.
Okay. So it says suppose we have a 200 milligram sample, so that's the starting point. That's how much we had in the beginning. We found R in the last one, so I'm just going to plug it in here. C. How much remains after 75 years?
You just use the PERT equation and set the time for 75.
It just tells you t equals 75. And so this is how much remains after t years, so I just plug in t equals 75 into that. So this is just p of 75. There's going to be 200 e to the minus ln2 over 30 times 75. After how many years will the mass be reduced to 1 milligram?
Oh, you solve for t, right?
Right, so how long is asking for a time?
Yeah.
Right, after how many years will pass? Which means you go back to the original, the time is what you don't know, so you have to plug in something else. We know that we want the amount remaining to be 1 milligram, but we know that P is the amount remaining, so you just plug in 1 for P. We're going to solve that for T. How do you solve that for T?
Divide by 200.
Divide by 200. Yeah.
Set both sides to ln.
Well, you plug both sides into the ln,
You
so you
cancel.
ln both sides. That'll cancel. Here you have ln of 1 over 200. Here you have minus ln 2 over 30.
Divide. You move negative ln to
Right, divide by that guy. So ln of 1 over 200 over minus ln 2 over 30. Or I can say my t is equal to minus 30 ln 1 over 200 over 2. Is that negative time? Does that make sense? Did we make a mistake? This time can't be negative, right?
ln 1 to the 200 is negative 5 point something.
Okay, so you get to this point, and you might think the negative sign might freak out, and so you might go, that would be wrong, because now you made it negative. Right? This guy is a negative number. How would you know that? You could plug in your calculator, but what's the intuition behind that being a negative number? Yeah?
ln fractions are always negative.
No, that's not true, because ln of 3 over 2 is positive.
Small fractions, less than 1. ln's a number less than 1.
You remember what the ln graph looks like?
It's like this.
Like that?
Yeah.
And what's this? It's been a while. What's the intercept? What's the x-intercept for the ln graph? Huh?
It's more.
You think it's 1?
it's
We
1.
need to know it's 1. It's actually 1, which means 1 over 200 is over here, right? That's a fraction that's less than 1. And so the output would be a negative number, right? So if you're taking ln of anything between 0 and 1, it actually gives you a negative number, right? And it bigger than 1, it gives you a positive number. So 1 over 200 is actually a negative number. ln of 1 over 200 is a negative number. Another way you could look at it is to realize that ln of 1 over 200 is the same as ln of 1 minus ln of 200, right? By the log rules, ln of 1 is 0, so just minus ln of 200. Hopefully you'd realize that ln of 200 is actually a positive number, so this ends up being. But either way, this is a positive number, and you should recognize that it actually makes sense to write that down. So hopefully you'll feel that in terms of what we've been doing before, these kinds of problems aren't that bad. One of the things you have to actually look out for is the fact that, when you're in a test, you're like, that was way too easy. It couldn't have been that too easy. And then you just randomly change something because you feel like that couldn't possibly be the answer. Yeah, that's what you have to look out for here. These problems will not be difficult in general, especially compared to all the calculus we've been doing before. It's just a matter of interpreting the words and plugging into the equations, sort of a plug and chug kind of thing, and recognizing when you actually have a meaningful answer. So this is actually a positive number. It does make sense, and that would be the time. As well as you can plug in your calculator and get a decimal approximation for it.
Is the exponential growth and decay going to be on the test?
On the third test.
Okay.
So, E. So it's problem 2, part E. So here I want the rate of growth when 1 milligram remains. What is that asking for? It's asking for the phrase rate of growth. What is that referring to?
Is it the slope of the graph?
Yeah, but which symbol in terms of
R?
It's not R. Right? Remember little r?
Yeah.
What is that called?
Relative growth.
Huh?
Relative growth.
Relative growth rate. This is called the relative growth rate. It's also called the growth constant. or I guess you can call it also the decay constant. Right, that would be the vocabulary for that thing. It would not be referred to as the rate of growth of the thing.
P derivative or derivative?
P prime. That's as for P prime. What is P prime?
Negative RT.
P prime is minus R times
T.
did we say P or T?
T.
It's P. So that's from I had it written over there, but that's that equation. So that's how you find the rate of growth. So now it says, what is the rate of growth when 1 milligram remains? So, which variable represents what remains? P, right? So P, I'm here going to plug in the number 1, because that's how much I want to remain. And R, we actually found that guy. That was ln2 over 30. Any questions on that? Let's move on to problem 3. So in problem 3, we have a bank that pays 5% interest compounded continuously. Never find a bank like that. And suppose you deposit $4,000 into this bank. Okay. So how do you know you should be using the exponential growth or decay formulas? Yeah.
Continuous.
Because of the phrase compounded continuously. Right. So it's compounded continuously, or continuous compounding. That tells you it's exponential growth. Which means the formulas, the set of formulas in the first box are the ones that now apply to this problem. Right? Those are the only guys you'll be looking at for this problem. And so, let P be the amount in the bank, or the balance in the bank. The units of the time here is years. So in part A, I want the differential equation with an initial condition that describes the situation. So what's the differential equation going to look like? Remember, the phrase differential equation just means an equation with a derivative in it, so that should sort of hint you what equation we're looking at. Huh?
Or B.
Well, it says equation, you have to write it as an equation. What is the equation?
P derivative RB equals RB.
P prime equals RB. Okay, so that's your differential equation. Okay? What's the initial condition? equation refers to the initial condition. Yeah?
P to 0 equals 4,000.
P of 0 equals,
The current deposit.
well, the initial amount. Okay. So you want to, so this question is asking for these two equations. The thing is, you need to fill in the R. You also need to fill in the P naught. In this case, the P naught is easy. They just told us right away that's actually 4,000. So that's not a big deal. But how do I find the R? What is the interpretation of R here? Okay, so this is going to be your interest rate. And you'd write it as a decimal. So in other words, what this question is asking for is P prime equals R. R would be what? 0.05. Because it's a 5% interest rate. So you just write 5% as a decimal. Remember, percent means divide by 100. So you take 5 divided by 100, you get 0.05. And the initial condition is this. So that's. At what rate is your account increasing when the balance reaches 6,000? What are we using here? What is rate of increase referring to?
Derivative.
The derivative. So we're going to use that derivative equation. And what do we plug in?
Plug in 6,000 for
So plug in 6,000 for. And whatever that is. How long will it take the principal to reach 5,000? So you deposit $4,000 into this bank that's paying 5% interest rate, compounded continuously. How long before you have $5,000 in the bank?
So you solve for t and
Solve for t in which equation?
per.
So I'm going to use this equation. What are the pieces here? What are you plugging?
5,000 for p. 4,000 for TL, P0. E. 0.05.
And so now you ask for how long, that's time, and you solve for time. How do you do that? Yeah.
divide off
That's correct. Divide both sides by 4,000. And at this point, it's kind of just like following your nose. You ln both sides. So here you have ln of 5 over 4 is equal to 0.05t. And so your t would be ln of 5 over 4 divided by 0.05. Any questions about this? So our next topic is related rates, but I don't think we should start it right now. It doesn't really get too far. So we can do this on Friday. Was there any questions about the test or the review or cool? Okay, I guess I'll see you guys on Friday. Bring your related rates handouts, because these word problems are a lot longer and we'll go over that.
The